Okay, I think now most of the registered participants are there. And I would say we start the session. Okay, good morning, good afternoon, good evening, everyone, ladies and gentlemen, from whichever time zones you are joining us. This is the kickoff event of the Laws of Nature discussion series. So we're very happy and delighted that so many of you showed interest and so many actually also joined the session. At the moment we have quite a bit more than 400 attendees and still rising. So I hope also in this distressful times during the COVID pandemic, everybody of you is doing all right. Your friends and family are healthy, and yeah, you somehow make your way through this very nicely. The aim of this discussion series, Laws of Nature, is basically to promote a seminar community in physics, philosophy, and mathematics. The, let's say, idea behind it is to connect the researchers, have exchange, and also focus a bit more on, let's say, a non-empty subset of the attributes physical seriousness, philosophical depth, and also mathematical rigor. So we have a very, we'll probably have a very colorful program of very different talks and very different formats, some in the language of physics, some in the language of philosophy, some in the language of mathematics. Some will be rather small, which we then take as a meeting where everybody can interact also with video and audio. Other meetings like today, where we have so many participants, we will use the format of a webinar. Basically, our program will be annually divided into two series, one spring series, one autumn series. You can have a look up on the schedule at the lawsofnature.net with minus signs in between the words. I'm sure you have seen the webpage already. There are also the Zoom links, and all other news and updates will be posted. So each of the sessions, probably around 4 per series, like in the spring series, we'll have 1 or 2 speakers. In case of today, we are very honored to have a very distinguished speaker who offered to start off the first event. And in a few minutes or in a few seconds, we will introduce him. Maybe a few words about the organizers. So there's, if you see now, Angelo Bassi in the panel view. Angelo Bassi is from the physics department of the University Trieste. At least on the upper hand side, I see Ward Struve. Ward Struve is from the theoretical physics and the philosophy department of the KU Leuven. And myself, my name is Dirk Deckert. I'm from the mathematical department of the LMU. And our moderator of the spring series will be Dr. Paula Reichert, who's also from the mathematical department of the LMU. And she will be the one who will guide you through today's session, and also hopefully, if we don't mess up today, through also the rest of the sessions in the spring series at least. So thank you very much for joining. I hand over now to Paula, and that you have the session.
Thank you. So welcome again. Welcome everybody to this new discussion series, which has been set up to contribute to the ongoing development in fundamental physics and to bring together those people who work in the foundations of physics, whether they come from physics, mathematics, or philosophy, and to have a platform for the exchange of ideas of the experts and students of the field. The series is structured into different sessions, and each session comes with a theme, with a motto. This first session has a motto which has originally been a title of a Feynman lecture, namely, "There is plenty of room at the bottom." So this shall remind us that there is still a lot to discover. This has been true at Feynman's time, and it is still true today. There is a lot to discover about the laws of nature and in particular about the interrelation of quantum theory and relativity. And there's one person who is intimately linked to these new discoveries and to this search for new physics. And I'm happy that he came here today. So it's my pleasure to announce our first speaker, a world expert in relativity and quantum theory, the man who has just recently won the Nobel Prize in Physics, Sir Roger Penrose. He will talk about how the large and the small interrelate in quantum theory and general relativity. And before we now start with the talk, let me just say a few words about how you can ask questions. For sure, all of you have noticed that you don't have a microphone or a camera, nor a chat function, but you have the possibility to pose questions in the Q&A. You can use the Q&A button, which you find in the column below. And there you can type in any question you have, and we will try to ask it for you. But please, during the talk, restrict this function just for technical questions, which are really necessary, you think, to follow the talk. And then we might be able to ask it in between. And after the talk, you have then the time and you are free to ask all other questions, because we then have a general discussion afterwards, and there will be plenty of time for all kinds of questions you want to ask. Okay, thank you. And now I'm looking forward to the talk. Professor Penrose, please.
Thank you very much. It's a great honor for me to be able to give the initial talk in this series. And I want to talk about the interrelation between quantum mechanics and general relativity. We normally think of quantum mechanics as the physics of the small and general relativity of the physics of the large. I want to indicate sort of relations between large and small, which may be a little bit unusual for people. One tends to think of quantum mechanics as physics of the small, and one often thinks of large things as being made out of small things. And so in some sense, quantum mechanics is more fundamental. I'm not taking that view here. I want to be much more even-handed between the two. Anyway, first of all, there are these two subjects. And secondly, if I can get these things to move, and it doesn't work, so let me try something else. There. We think of them rather separate from each other. Quantum mechanics on its own and general relativity on its own. I want to start thinking about the interrelations between the two, so we can consider, first of all, what is there in the relation between the two. And well, often people, as I say, if you think of quantum mechanics as more basic, people tend to use the techniques of quantum mechanics to try and discuss general relativity. So here on the left, I've kind of indicated something like Feynman diagrams, where people use the techniques. Feynman himself was one of the very first to consider using Feynman techniques or techniques of quantum field theory to discuss general relativity. And in fact, that's a big subject, a lot of activity in that area, not to be, I don't want to play it down at all. It's very important, but I don't think it tells us too much about general relativity. For example, if you want to talk about black holes, I mean, mainly you're talking about perturbation theories and things like that, and you're a long way of being able to discuss things like black holes. So let's move on. And in the other direction, one can have, let me just see if yes, here we go. The things don't move when I want to play them, so I have to see if that doesn't move. Ah, here we go. Oh, moved too far. Sorry. Never mind. I can't get it doesn't click on it and it doesn't do it. It's quite beyond me what's happening. Never mind, this will do. I was talking about yes, here we go. Quantum mechanics within the framework of general relativity. This is basically you're going to do quantum field theory in curved backgrounds. And that's, again, a perfectly respectable subject. The trouble is here, you don't have any back reaction. You can do quantum mechanics to some extent. There are problems, but you can still think of doing it. I would say the most important application of quantum mechanics in general relativity is Stephen Hawking's picture of the black hole, where he does quantum field theory in the black hole background, and he comes to the conclusion that there is a temperature to a black hole. And this temperature, if you imagine a black hole, in this picture is a space-time picture, so time is going up the picture, and we have at the bottom collapsing material, and we have the null cones drawn in yellow. And as we follow up the picture, you see the horizon, and you see the singularity in the middle, and you see the Hawking evaporation, which carries away very, very slowly energy from the black hole. In fact, it will take an enormous length of time. For the largest black holes we know there, it will take something like 10 to the power 100 years, or what people sometimes call the Google years. A little bit more, according to a calculation of Don Page, 10 to the 103, I think was his number. So you have to wait an awful long time before all the black holes disappear, which according to the Hawking evaporation, they will eventually disappear. Now, this is an important consideration, which we'll come back to later, but let me move on to something more where we consider the whole theory, a more general theory, which would encompass both. And there are lots of ideas here. There's strings, and there's loops, and there are foams and things like that. They're very far, well, whatever you think of these different theories, and I'm not very confident that any of them is really telling us what's going on, but they are certainly very far from anything like an experiment. So if you want to see the implications of any such a theory as an experiment, we're not seeing it. So we're very far from it there. I'm not going to talk about these theories. What I want to talk about is something else. I want to talk about the problems that each theory has. So here I have, on the left-hand side, we have a cat which is half dead and half alive. You see, that's meant to indicate what I regard as the fundamental problem of quantum mechanics, the measurement issue. I want to first talk, however, about the right-hand side, which is the problems that general relativity has. These are internal problems that each theory has, not necessarily, obviously, one to do with the other. Nevertheless, I do believe that in order to resolve the problems of each side, you do have to look at the other theory. And it's quite accepted that in general relativity, we have this problem of singularities. In black holes, as long as you don't have, well, very large deviations from positive or non-negative energies and things like that, you're bound to have singularities. And what you must expect is that in a black hole, the collapse will cause curvatures to increase and increase and increase. And maybe you'll get to a stage where people say that quantum mechanics comes in, which would be when you have curvatures, the radii of curvature, which is down to the Planck scale, 10 to the minus 33 centimeters, something like that. Well, we don't really know anything about what goes on there, but you would expect quantum mechanics to come in. Whether it resolves the singularities or not, it doesn't answer the question. When I say it doesn't answer the question, let me consider what the question is. I want to go to the next slide. The problem with the singularities from my perspective here, see, in the old days, I was studying how general singularities were and that the symmetrical case of Schwarzschild collapse, where you have spherical symmetry, it's not so surprising you get a singularity because everything's focused into the middle. But if it's irregular, you can show that you still get singularities. And what you expect is that the curvatures will get bigger and bigger and diverge to infinity. It's not just the curvatures, it's the Weyl curvatures. Now, when I talk about the Weyl curvature, I'm talking about the conformal curvature. The curvature of space-time basically separates into two parts. The part which is directly caused by the matter, that's the Ricci curvature, and the degrees of freedom, which are the gravitational degrees of freedom, which are given by the Weyl curvature. So you have these separation into two parts, each with 10 components. And what you find in the singularities in black holes and the general case you'd expect is that the Weyl curvature blows up and becomes infinite. The gravitational degrees of freedom simply dominate and they diverge and become infinite. So that's what happens in the singularities in collapse. What about the other direction in time? Well, again, when I was talking about singularities in the early days in the mid-1960s, Stephen Hawking picked up on that and applied many of these techniques to and generalized them to the Big Bang singularity. So we have this big singularity in the past, and you might say, well, the techniques apply one way or the other because the singular problem is just as much in the past as in the future. That's true. But when you look at them in detail, it's completely different. That is to say, we expect in the past, the Weyl curvature goes to 0 rather than to infinity. And I want to say a bit more about this because this is the key issue which I want to address to begin with. Here I have a picture of the universe. Well, we don't know whether it's spatially open or closed. And at the back, I sort of am a bit ambivalent about that. It doesn't necessarily close up, and I've drawn it a little ambiguously that it may close up or it may not. That's not important for what I want to say here. I'm drawing it so it looks rather closed up because it's easier to draw the picture there, that's all. Okay, so we have the Big Bang in the beginning, the expansion, and then we now have beginning now, we see this exponential expansion, which looks very much like a cosmological constant in Einstein's equations. And I certainly treat it as a cosmological constant. That's the easiest explanation for this remote expansion. People sometimes think you need an explanation for the cosmological constant. Well, maybe you do, but at least the cosmological constant seems to explain very well what we see in this remote future. But what about the past? The Big Bang, that's where we get the singularity. Now, in this case, well, I should go on to the next picture because people argue that perhaps what smooths out the singularity, it's something which is very smooth in a certain sense. It's very uniform, and that maybe there is something going on at the beginning, which is referred to as inflation. So current cosmology postulates that there is an initial stage, which is inflation picture, which is, I've now got a magnifying glass. I don't know, I wanted the magnifying glass first here. Here we're having a look at the Big Bang, and do we see inflation? Well, if we do, according to the inflationary theory, you see an exponential expansion again. I want to point out one thing here. It's one of the reasons for inflation is to address the question of the microwave background and the fact that you have a pretty well scale invariant feature. The deviations from constant temperature are scale invariant pretty well. And one of the explanations is you have this early stage in the universe, which is inflation. Well, okay. I never liked inflation because it seemed to me a very artificial theory. And people also argued it smooths out the universe. So you might imagine it was very irregular to begin with, but then the inflation smooths it out. I want to argue that this is not the case. And the argument is the following. Suppose you imagine a collapsing universe. Just turn my picture upside down. So a collapsing universe, what will be the general case? Suppose there were perturbations in this universe, lots of irregularities. These irregularities would increase. You get black holes. The black holes will combine together. And instead of having this rather nice uniform singularity, inflation or not, you can put your inflation field in at your will. It doesn't make any difference. What you get is something like this, a great mess at the end. That great mess was much, much more likely to happen than, I mean, by a huge factor you can work out by looking at the entropy of a black hole, and the calculation you get is something like the probability of it being like the smooth universe we just saw, as opposed to this great mess, is something like 1 in 10 to the power 124, something like that. So you're looking at an extremely unlikely situation if it was just by chance. So it wasn't just by chance. Let's go to the next picture. That's to say, why didn't we see this? The singularity theorems would tell you get a great mess like this in general, but it doesn't tell you that you get a universe with or without inflation. The inflaton field only makes a difference if you're very close to what you want anyway. So it doesn't really help very much. So this is what we have, and we've got to explain it. Well, I say that the argument cannot be simply quantum gravity, because quantum gravity, whatever it was, if it got rid of the singularities in the future, that great mess that we saw, it's got to do something completely different here, because getting rid of that singularity isn't going to produce this nice smooth situation. You've got a nice smooth situation, that is to say very regular, spatially regular, and not with the Weyl curvature going to infinity, but the Weyl curvature probably pretty well zero. Now, this is tied up with the second law of thermodynamics. It's very fundamentally tied up with the second law of thermodynamics. In fact, it really is the source of the second law of thermodynamics. The top three pictures, I'm imagining a gas in a box. And I imagine, first of all, that gas is contained in a small compartment in the corner of your box. You open the compartment, the gas spreads out. And so increasing entropy goes with increasing uniformity. The bottom is now considering a huge box containing a lot of stars or something like that. And these stars, we're thinking now of gravity, whereas the top was most ordinary physics, say. But if we think about gravity, being a universally attractive thing means that the entropy goes the other way. That is to say, with increasing entropy, you increase the clumpiness. So left to right is increasing entropy in both cases, but it's very different in appearance. What we see in the early universe is uniformity. We see something like high entropy in the matter, which is certainly confirmed when you look at the microwave background and you look at this very nice Planck curve. It very confirms that you have very, very high entropy in the matter or in the radiation. When I'm talking about matter, I mean electromagnetism as well, radiation. Whereas the gravity, it's the other way around. You see a top right and bottom left. So it's not just that the entropy was small in the beginning, it's small in this very curious way that gravity was singled out as being the one thing that was not thermalized. So that's what we're presented with. Now, what about going back to our picture? I'm going to look at it now in a different way, which is rather useful to think about. What is the geometry of space-time? Well, the geometry of space-time locally is determined by the metric. And the metric, we have a light cone here, or null cone. And in this null cone, I have these surfaces of, so imagine that these are two particles zipping along, and they're little clocks. And the first tick of the clock and the second tick were these hyperboidal surfaces. So you add to the null cone the structure given by the hyperbolic surfaces. And I'm combining at the bottom of the picture the two most famous formulae of 20th century physics: E equals mc squared, that's Einstein; E equals h nu, that is Planck. And you combine the two and you see that frequency, that's the nu, and a mass are basically equivalent. So this means that if you have a massive particle, it's a clock. So that the metric is very clearly to do with massive particles. Massive particles are essentially clocks. They're very, very high frequency. You have to tone them down a bit in order to get nuclear and atomic clocks, but basically they do depend ultimately on this relationship. So that we have the structure of the metric is given by massive particles, but suppose you don't have any massive particles. Suppose you just have massless particles like photons, then you don't care about these bowl surfaces and hill-like surfaces, and you're just concerned with the light cone. So massless things are interested in the light cones. In other words, that is the conformal geometry. The full geometry, the metric at any point has 10 components. 9 of those, or basically the ratio of those 10 components, that's 9 numbers, define the light cone. And if you have massless things, they're interested in just the light cone. If you have mass, then you have to extend this to the one extra component, if you like, the one extra number, which gives you the scale. But if you have massless things, then basically they're interested in just the light cones. Now, the moral that I'm using here of that is that you have the freedom now to look at conformal geometry. Now, conformal geometry in relativity theorem, as I was just saying, is the light cones. But if you are looking at the picture that I'm showing you here, this is a nice, wonderful one of these circle limits due to the Dutch artist M.C. Escher. And very beautifully, he had got the idea from Coxeter. He didn't know about it before Coxeter explained, and then Escher made these wonderful, amazing prints. This is actually the first one. It's in a sense the most clearly related to the mathematics, because you can see these fish-like creatures, their eyes are exact circles, and they remain exact circles right up to the edge. So conformal geometry preserves shapes, but small shapes, but it does not preserve sizes. So here we have a geometry which is hyperbolic geometry. You don't need to worry about the particular geometry, but the point about hyperbolic geometry is you can squash it down in this conformal picture, basically due to Beltrami originally, and he has this description, and you can see the Escher representation of these little tiny fish if you magnify them up. And if you look at the Escher pictures, they're amazingly precise, right close to the edge, and you see the shapes, the angles on the fish's wings or whatever they are, fins, are the same no matter how close to the edge you get. Angles are preserved, but size is not preserved. And in relativity theory, the light cones then, this geometry of the light cones is a conformal geometry. So let me go on and talk about cosmology now from this perspective. Now you see, like using the Escher trick, I can squash down the remote future. And when you have a positive cosmological constant, as we seem to have, you have a space-like infinity. And I've drawn it here. Of course, I had to throw away 2 dimensions, but imagine this is really a 4-dimensional picture. We have this top boundary, which is a 3-dimensional space-like surface, which represents the infinity. And in fact, this is a very good description. Wonderful theorem by Helmut Friedrich tells you that very, very generically, you will get this very smooth conformal infinity if you have massless ingredients in the space-time. What about the other end? Well, this was a trick which basically was due to my student, Paul Todd. I had a criterion, which is just say, well, hypothesis. What is it that the Big Bang has to be that characterizes it as being different from the generic singularities in the future? The Weyl curvature vanishes. So my hypothesis was past singularities have vanishing Weyl curvature, future singularities can have wildly diverging Weyl curvature. It's just a hypothesis. I used to think that quantum gravity had to be some wildly crazy theory in which it was blatantly time asymmetric. That was my view, and I couldn't see what kind of quantum gravity it could be. My view now is very different. My view now is it's not quantum gravity, that the quantum gravity is not the answer to the Big Bang singularity. The answer is that you have to study conformal geometry. And the conformal picture, according to Paul Todd's way of rephrasing the Weyl curvature hypothesis, is that you can stretch it out by a conformal factor and make it to be a nice, smooth boundary. Now, going slightly beyond what he was suggesting, I now want to consider why was that nice, smooth boundary there in the first place? Well, because it was the continuation of a previous remote infinity. So this is my conformal cyclic cosmology picture. I have a lot of trouble convincing people that it's a good picture. The first thing, of course, you have to convince people about is that it makes sense, first of all, geometrically. I think that's very clear, that it's not outrageous geometrically, because if you stretch out the Big Bang, you get a vanishing Weyl curvature, and this vanishing Weyl curvature is a generic feature of what you get by Helmut Friedrich's ideas of the remote future. You get that as well. And so you can patch them together. It seems that this is reasonable. What about physically? Well, physically, you might think, well, the future is very, very cold and very rarefied, whereas the past is very hot and extremely dense. Aren't they extremely different? Well, you see, when you stretch out the Big Bang, the stretching has the opposite effect on the momentum and position do the opposite things. That is, when you make the distances bigger, you make the temperature smaller. And so you stretch out the Big Bang and it makes the very hot thing very cold, much, much colder. What about the future? Well, it's very rarefied, and when you squash it down, it becomes hotter. So it's physically reasonable too. They might match. The one little problem you have is that the remote future is not just photons. This would make this a very clear picture. You do have hydrogen and various particles hanging around too. So I have to introduce another hypothesis, which is that the mass will gradually fade out in the remote future. It's not so unreasonable when you think about how you characterize particles. You use the excuse me, the Poincare group in order to characterize particles in the past. And when you have a cosmological constant, the characterization is a bit different. And the things which are conserved are not quite the same. And you might say that perhaps mass, Casimir operators, you have Casimir operators, which are the things which are absolutely conserved. And when you have a cosmological constant, that's not quite true. So if you introduce that, you might imagine that maybe mass is not actually. That's a bit of hand waving there, and I don't know of a better reason for arguing that the mass may fade out, but this is the main hypothesis, is that the mass fades out, and you do get dominating zero mass things in the remote future. What about the Big Bang? Well, there it's much clearer, because there you have the temperature gets enormously hot, and then the mass becomes irrelevant, because the higher the temperature, the less relevant is the mass, and so that the mass becomes completely insignificant. And so you might as well consider that asymptotically, as you approach the Big Bang, particles become massless. So this is the hypothesis, and this is the picture. Now the picture does have many implications. I can think of at least three things. Let me not mention all of them, or four things I can think of. Let me mention the first thing I wondered about. First, I thought nobody would ever be able to disprove me, so I can go on arguing about this forever. But then I did think of arguments. This is a picture of the crossover surface between one eon and the next. I call these things eons, each one of these stages of the universe, starting with its Big Bang and ending with its remote future, is an eon. Here we have the remote future of the previous eon, and this is our eon. And after it, the plane in the middle is meant to be a three-dimensional surface, which is the crossover surface between the previous eon and our eon. Now you imagine in the previous eon, you have a collision between supermassive black holes, such as what will happen when our galaxy collides with the Andromeda galaxy, and our relatively small supermassive, well, black hole in the center will eventually be swallowed up with a much bigger one in the Andromeda galaxy. And this will, to the people in the next eon, this maybe we'll see the effect here. Now, what is the effect? The collision will produce a gravitational wave signal that spreads out, and the intersection of this sphere here and our past light cone sphere will look like a circle. So you will see circles, and Vahe Gürsejan, my Armenian colleague, looks at these things with a rather ingenious way. He looked at low variance. The temperature variance should be small around the ring, and you have to look at least three of these to get a significant signal. You see, I'm imagining that in one galactic cluster, there will be several big collisions between supermassive black holes. Ours is a relatively small one. You'll have bigger clusters where there'll be lots of these collisions, bang, 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 like this, spread over, of course, many years, zillions of years. But when we look back, we will see big rings, and smaller rings. They will be concentric. So that was what he looked for. And I'm going to show you in my next picture something rather remarkable. These are looking.
Sorry, Professor Penrose, may I just intervene and ask a question?
Yes, please.
To what you said before. So there was just one question on the conformal geometry approach you just sketched. Right. And it was the question, does approaching the answer to the shape of the universe from the perspective on conformal geometry, as opposed to loop quantum gravity, imply the tree torus model of the universe?
The three-class model?
Tree torus. Tree, like a tree, torus model
I have no
of
idea. I think, are we talking about Hoof's model by any chance? I don't know. No, I'm not using any string theory or anything like this in this model. I don't have any predictions about whether the universe is spatially open or spatially closed. That maybe there will be eventually, but there are no predictions here of that sort. I don't think I can answer that question because I'm not sure I know what the model is that's being talked about. Is it the Hooft model?
No, I think if the person who asked the question, he or she might clarify it in the general discussion afterwards.
Let's leave it for
Thank you.
It doesn't say anything about that. However, what we do see is in the Planck data, we see this also in the W map. I'm sorry. Yes, the older W map matter, but I'm talking about the Planck data. This is the more specific later satellite, which was looking at the microwave background and analyzing it in the way which I was just indicating, looking for low variance concentric rings of at least 3. And these are plotting the centers of these rings. Now, what you see is not a uniform distribution of a whole sky. Whatever the explanation for it, you see a non-uniform distribution. This is rather saying that there are super duper clusters. On these super duper clusters, now notice the color. Now the colors indicate the temperature. I would tell you first of all that these rings were not selected for their average temperature, just for the low variance in the temperature around the rings. The red ones are the warmer ones, so the blue shifted. It's all very confusing because red is blue shifted, and it's doubly confusing because in the theory, the blue shifted ones are the more distant ones. I won't go into the details of that, but the red ones would therefore be very distant. The blue ones are not so distant. They're pretty far away, but they are inside what we call our particle horizon. The red ones are, according to the theory, outside our particle horizon. We shouldn't be able to see them at all in ordinary theory, but we can see them in this theory because we are looking through beyond into the previous eon. I don't know if I could explain it in this picture here, but as you look back, your back cone crosses over into what you couldn't see in the ordinary theory. Let me not go into that in more detail, but the red ones are very, very distant. The point I'm making is that they're clumped in color, not just in where they are. Color means, in the theory, distance. So there is a big, huge, enormous, super duper cluster of galaxies in this picture. The blue ones are less super duper, but pretty super duper within our past light cone. They're within our event horizon. These ones are sort of intermediate down here. So any theory that you have to express these things will have to express why they are inhomogeneous to this degree. I don't know of any other explanation. It's a clear explanation from the CCC model. It does require that you have a less uniformity than people think in the universe on the very large scale. But nevertheless, that's what we have. Okay, now another feature is coming from the evaporation of black holes. As I say, these black holes will evaporate away, and what happens to them in the very remote future? Well, this is a picture from a paper written by Christoph Meissner, Pavel Nurovsky, Daniel Ann, and myself in the monthly notices of the Royal Astronomical Society, published about, 9 months ago or so. And here we have the bottom horizontal line is the crossover surface, according to our theory. And the next line here is the last scattering surface, or the decoupling surface, more or less in the same place. Now here we have a line coming up, which this is the previous eon down beneath the horizontal line. And here we have a line going up, which is the history of a supermassive black hole. Its evaporation away will be right at the end. Because it takes so long before it evaporates away, it's squashed into a tiny little point. That tiny little point will be the entire energy of that evaporating black hole. So it will be an entire supermassive black hole, probably a big galactic cluster, all squashed into one place. That much mass. That then spreads out through the 380,000 years, that's the basically Nobel Prize last year, which was Jim Peebles and company, and they had wonderful work to show what happens in this, basically this region, and what we see here on the last scattering, these coupling spaces right here. And here we have, therefore, this energy here coming through that point was spread out, and you get something like, I've got the top here indicated, something like a Gaussian distribution, where the light, that's basically this energy doesn't escape, it just scatters, and it spreads out, and finally it reaches this distance, which is about 4 degrees across the sky. When you look out at the sky, this would be about 4 degrees. That's 8 times the diameter of the full moon. So you would see a spot in the sky, which is warmed up to, well, it turns out to be about 30 times, the biggest one, say about 30 times the average temperature variations. And we see these points. And what's rather remarkable is that they've never been seen before. I think the reason they've never been seen before is simply that nobody's bothered to look. They don't look because they expect that inflation would have smoothed out the universe, and therefore you wouldn't see things like this. If you look for them, you see them. They're in the Planck data with a confidence level of 99.98%. That is to say, the signals are there to that expectation. You can actually pick out the strongest ones. The 99.98% doesn't actually tell you where they are, that you have to look with a different kind of algorithm. And I think these 5 strongest points that you see in the Planck data, you see them also in the WMAP data in exactly the same spots. There is another one in the WMAP data, which is also very strong, and you look at back in the Planck data and you see that's there too. So those 6 points, I would say, are pretty good candidates for being what I call Hawking points. This is the actual Hawking point, is where all the Hawking evaporation or all the mass, whatever form it takes, will be squashed into that point. It spreads out to 8 times the moon's diameter, and you see this warmed region. And as I say, they're there. And you can also see a correlation between the Varses rings and these to the sort of degree you expect. I don't want to go into that here, though. Okay, let me move on to now the other part of my picture. I was just talking about the singularities. Oh dear, I haven't got the hang of making this work. Takes a while. Okay, now I want to talk about the other side. I hope I've got some time to talk about the other side. I started a bit late, so I hope I have the time to talk a bit about this, because this is an important subject. The measurement problem. Now, you see, my take on the measurement problem is that we need new physics. It's not somehow interpreting the physics or something else. There is something new, and not just any old new physics. The new physics is how it combines with general relativity. Why do I say that? Well, what are the two basic principles of the 2 big theories? The basic principle, I would say, of quantum mechanics is the superposition principle. The basic principle of general relativity is the principle of equivalence. At the top of the picture, we have imagined Galileo, or somebody, if it wasn't Galileo, an imaginary person dropping a big rock and a little rock, and the big rock and the little rock fall together. And according to Galileo, a little insect sitting on the big rock would see the little rock as though there were no gravity. He perfectly well understood this aspect of relativity, which was an amazing insight. The insight is now confirmed very much by space travel. Here I have a sort of 2001 type space station and an astronaut. Despite the Earth being there, the astronaut doesn't feel the Earth's fields, because falling freely, you don't feel it. So that is the principle of equivalence, a very basic principle. Now, let's think of those 2 principles together. And what I'm trying to do now is imagine an experiment on a tabletop. Here is our tabletop, and then there's an experiment. And this experiment involves a massive object. Well, you want to consider the Earth's field, and there are 2 ways you might do your quantum mechanics. One way is the way any normal physicist would do it. You just put a term in the Hamiltonian. You imagine that gravitational field is like any other field. You put a term in the Hamiltonian. That is using coordinates, which are the normal Newtonian coordinates, say, in the frame of the table. Now, the other way of doing the gravitational contribution, if you want to take the Earth's field into consideration in your calculation, is to consider a freely falling field. So that is the Einsteinian perspective as opposed to the Newtonian one. So the green coordinates are the Newtonian perspective, the purple ones the Einsteinian coordinates. There's a simple translation which goes between one and the other. And you have a term in the Hamiltonian for the gravitational field in the Newtonian one. You don't have it in the Einsteinian one. Now you do a calculation and you find that there is this simple relation between the two. There's mere phase factor between the two. So you might say, who cares? A phase factor, you're only going to take squared moduli of things anyway, so you might as well do one or the other. But then you look carefully at the phase factor and you see it actually does make a difference. There's a t cubed in the phase factor, which tells you that you're in two different vacua. If you did a Fourier analysis or something, you would different positive negative frequency decomposition. The vacua are different. Again, you could say, who cares? Stick to your vacuum and it makes no difference. Okay, that's fine. However, now I'm going to change the problem. I'm going to put a mass in the situation which isn't just a passive body, it's being moved as part of the quantum system. So the body is now in a superposition of the blue one and the brown one. So the body has superposition of two locations. And then you try and do this, well, locally, you would try and do this and you see you have this slight difference in your vacuum. You can't do it because it's inconsistent, but you do your best and you say, well, you've got two different gravitational fields here and you do your best and you see what basically you find basically an incompatibility with your vacuum, which you try and say, well, it's a sort of error in the system. And then you integrate that error over the whole of space and you find out that this integral is what I'm calling EG. This error turns out to be, this is just showing you in space-time terms that your little problem that you try to fall freely and you do it once, but you can't do it in superposition between two fields here. Let's move on. Not quite sure what's happened to my, oh, I see, it's gone back. There's a time delay when I press my button, which is irritating. Okay, now what you come to is this hypothesis of a rate of collapse, which is given by a formula which was due originally to Diocchi. I wasn't aware of his when I did it, but he did it first by quite a while. This is an estimate of how long a system will survive before it decays into one or the other. So I'm imagining that this error, EG, which I've called, you work it out and it turns out to be the gravitational self-energy of the difference between the two gravitational fields. So you've got a gravitational field here in superposition with one over there, and I'm supposing that each one is a stationary state. And I take the difference between the two, and the gravitational self-energy of that difference between two gravitational fields is this thing EG, which is the same thing that Diocchi considered. And the lifetime, I'm considering EG to be a fundamental uncertainty in the energy of the system. And therefore, by the Heisenberg time-energy relationship, which is normally applied to an unstable nucleus or something like that, you say the lifetime of that nucleus is reciprocally related to an uncertainty in its energy. And I'm using the same formula, but the other way around now, saying if I have an uncertainty in the energy, which is the EG, then its lifetime is given by H cross over EG. So that's the hypothesis. And this is the Diocchi original hypothesis, which I'm phrasing in this way. This is just a little calculation to show what happens to the uniform sphere. And if you move a uniform sphere into a superposition of two locations, what is the EG? And what I'm trying to indicate with this formula at the bottom is that about 2/3 of it are moving it from coincidence to contact, but there's still quite a bit left from contact out to infinity. And if you imagine two spheres out way apart from each other, then it's quite likely on this theory that the collapse would take place when they are well separated. So let's suppose that's the case. Now here I have a space-time picture, and I have at the bottom the body sitting there, And then it's put into a superposition of locations. And as these locations separate, then I imagine that they are in a superposition between the two, and then they collapse to being one or the other. Now, if the collapse is regarded as something instantaneous, which I do for various reasons, which I probably can't go into here, if you had a gradual one, you might be able to get away with it by having an amplitude which fades out and the other one increases according to the sort of CSL type scheme. If it's a sudden disappearance, which is the point of view I am adopting, then you have a trouble with relativity, because here I've got, imagine the observer moving off up in the leftward direction, and then if it was a very high speed, then the A0 surface here, and then the A1 surface, I put it cleverly where one of them is still there, and the other one is already decayed into the other position. So if this one disappears and that one's still there, it's not consistent with relativity. It's only consistent with relativity if it goes right back to the beginning. So the picture I'm having that is what happens. And I'm trying to explain this picture. I'm probably having to rush rather, and I'm not sure whether I can make it clear. It's not moving now, so I have to move it this way. I hope I can do it that way. Okay, here we go. This is the picture I have. Now, I'm imagining at the bottom here we have a laser emitting a high energy photon. It encounters a beam splitter, half silver mirror or something, tilted at 45 degrees. So photon half goes through and half is reflected. Now, if it goes through, this part of the photon's wave function hits the body, starts to move it. As you work your way up the picture, the space-time, you see I've got a little kink in the space-time, it moves up, the space-time bifurcates to become two different space-times. And when it comes to the sort of the Yoshi point where you would expect the decay to occur, one of them disappears and the other one creates the future. Now, the picture here, I'm illustrating two different kinds of reality. Now, I want to talk about that. Let's move on to the two kinds of reality first, because I think that will, here we go. Classical reality and quantum reality. Now, classical reality is the sort of reality we normally talk about. The space-time basically will evolve basically according to the classical reality. Classical reality of a system, the difference is there's a sort of ontological distinction between the two. Classical reality, you can ask a system, what is your state? And the system can say, well, my state is that, thank you for asking, my state happens to be X. Quantum reality, you can't do that. Quantum reality, the best you can do is you can have a theory of what you think the state ought to be by now. This is what I'm calling Einstein's dictum. Einstein had this criterion for reality, which is a kind of reality I'm calling quantum reality. That if you can ask of a system, is your state X? And if the answer comes back, yes, my state is X, and it answers that with certainty. So you repeat this system many, many, many times, it always comes out with the answer yes. So it is a reality, but it's a weaker sort of reality. It's the quantum reality. Let's imagine you have a spinning, say a spin half particle, and you don't know which direction the spin is in. Then you might choose the direction and it'll only give you a probability it's that way, and a more probability it might be the other way. But if you have a good theory which shows you think it's in such and such a direction, you measure it in that direction, and it comes up with the answer yes every time. So it is a reality, but it's not quite the same reality. And I'm trying to distinguish between these two realities because I can't quite remember with my next picture. I'm not having much luck with making these things move properly. But let me go back to the previous one. I hope it will give you that. It's not giving you that. Oh, here we go. Okay, now you see the quantum reality keeps the superposition going. And so you have this lump in these two locations at the same time. You could sort of confirm that by doing an experiment. It would have to be a tricky one. You'd have to pick up the photon which has gone the other way and do an experiment which would confirm that it is in the superposition. So in principle, if you actually do the experiment, that wrecks it, because doing an experiment may change the quantum reality, may change the classical reality too. But if you did the experiment, you'd know you would get the superposition. However, when the choice is made of which way it goes, then you have to say that choice had been made right early on, right down here somewhere. So it's as though all the time the universe follows the classical reality picture. It's a strange way that I think it's important to make this distinction, though, because it does, you see, many theories which do go beyond standard quantum mechanics and perhaps introduce like these CSL models, or the model that Diyoshi was promoting, for example, where you consider that the collapse really is happening here. That is to say that the thing jumps from here to here, then you get small jumps all the time when reduction is happening, and these small jumps cause a heating. And this heating should be observable, and so far it's not been observed. In this picture, you don't expect the heating because the jump goes right back to here, and it's as though all the time it had followed the other route. It looks, you have to worry about, is this an inconsistency? It's not. You have to think pretty hard about this. I don't think it does lead you to an inconsistency. I think the picture, yes, this is actually quantum reality. I was just indicating the Einstein dictum, which is that if you, without disturbing a system, can make a measurement where the answer with certainty is what you're asking, then that gives you a quantum reality. Actually, the quantum reality sort of fades out because the longer you wait, the more the chance is that it might reduce, and therefore it's not quite certainty. So you have to worry about that. This is a picture of quantum reality in an EPR situation. At the bottom, I'm imagining you have a spin zero system which splits into two spin half systems, and here's Alice over this way and Bob over there, and then you can work it all out, and it's a perfectly consistent quantum reality, which is quite strange, but nevertheless, that's what the picture illustrates. Have I run myself out of time? I think I have, so I should better stop, I think, at this point. I'm not sure. This will do. I had some experiment that one might be perhaps.
But please take your time. If you need some more minutes, you can.
Let me just indicate the experiment because I think it's interesting here. This is a hypothetical experiment. And people ask me sometimes, could you design an experiment to test this retroactive picture? When I say retroactive, that is the classical picture goes back to what it was. Now, I'm not sure you can exactly, but what you can indicate is how puzzling real quantum mechanics is. The retroactive picture does give you an explanation for it, but you might be able to hold to some other view. Here I have a laser, just in the previous picture. The laser emits a photon. Here we have a beam splitter, or half silver mirror, if you think of it. And the photon is half transmitted and half reflected. Here we have a mirror, which reflects it back. Here we have a mirror, which reflects it back. The thing is set up that when these mirrors reflect it back, it simply goes back into the initial laser, and a detector down here does not see it. Okay, so that's the picture. And I could say that there's a little bit of a spring on here because maybe there's a reaction on the photon on the mirror, and it may slightly reduce the frequency. And this thing, I'm compensating for that over here because I have also a little thing, it's a little catch. It's slightly, there's a little tiny catch, which doesn't take much to release it. The little piece of the photon's energy which you're removing here would be enough to release this lump. So there's a lump of material which starts falling. So if the photon has come this way, the lump starts falling. If it's gone the other way, the lump doesn't start falling. Now, if you're just considering a quantum system and you're considering the lump is still in a superposition of falling and not falling, it can still be a superposition and the photon's in a superposition, and it doesn't make much difference which way it's gone because the amount of energy is taken from the photon is the same and it goes this way. So as long as you've not made a measurement on this thing, it goes this way. But suppose this is a big whacking great lump here. According to the state reduction in terms of mass displacement, yes, the state would reduce here spontaneously. If it reduces, then it's either gone or not gone. Either way, it means that this photon has come this way, and that means that it's a superposition, this mirror of going this way and this way. And so there is a 50% chance that a detector down here will see it. If the lamp is not reduced, then you will not see it down here. Now it might reduce because it's got mingled up with the air. Maybe there's no air there. Maybe it's completely rarefied and blah, blah, blah. It's a bit hard to see how this can, I mean, according to standard quantum mechanics, if some measurement is made, then you can get a detection here. If there is no measurement here, and the measurement might be made quite late, is it before the detection? Is it after the detection? It's very puzzling to me that you could have something which makes so much difference if, well, I mean, if it's a state reduction because of a lump moving here, then that would give you the answer. I think it's the answer that standard quantum mechanics could give. But if you have an answer, a theory which is to do with some displacement of material or something, it's hard to make this make sense. I just want to throw this experiment out because I think you have to get the right answer being that if the measurement takes place, if the lump actually does get displaced in this superposition and then becomes one or the other, then it allows this thing to detect the photon. If that doesn't happen, no, it would go out this way. But that's what standard quantum mechanics would do. But does your theory of modifying quantum mechanics give that picture or not? That's the question. The retroactive one does, because it tells you that when the lump goes into one or the other, you've got to trace it back, and you trace it back to here, and it says, yes, the superposition is allowing this to take place. Let me leave it at that, and I'm quite happy to take questions at this point. Thank you very much.
Thank you, Professor Penrose. Thank you for this great talk and for the beautiful pictures you showed to us. So now let me explain just to everyone again how it now works with the general discussion. So you will be able to type in a question in the Q&A below, and we will then see it and go through it. And yeah, Professor Penrose will try to answer it to you. And maybe just for all of you, once the question has been answered, everybody will see the question and also the name of the person who asked. But you don't see it before.
Will I see it?
But you see it, and also I will read it to you. Okay, so shall we start?
Okay.
All right. Yeah, I think, Paula, we have the first couple of questions coming in.
Yeah. Okay, so I start with the first question, and
I hope you can read them because I can't see them.
Yeah, I will read it.
Yes, thank you.
So the first question is, what is your take on Dragan and Eckert paper on quantum principle of relativity?
Sorry, whose paper is this?
Dragan and Eckert paper. Do you know that?
Oh dear, I'm not sure I do. What did that say?
So I'm not sure either. Does any of you know?
No, I would say let's move on to the next question.
Let's go to the next question then. I mean, the person who asked the question, maybe he can.
This is Arthur Eckert.
Yeah, make it more clear. So next question then.
I need to know what the question was. Yes, yes.
Okay. Now we see that was now again to the question which was asked in between. So I read it to you. I was referring to the torus model. I think the 3 torus model proposed by Zeldovic and Starobinsky, which describes the shape of the universe as the 3D torus. I was wondering if what Professor Penrose said about the answer to the shape of the universe lying in conformal geometry instead of quantum gravity has anything to do with the torus model, and if not, then what can conformal geometry tell us about the shape of the universe? I hope this clarifies the question from before.
Okay, so that was a different thing from what I thought it might be. I mean, it's quite a separate issue. The issue here has to do with, I suppose, the large-scale topology of the universe. Are we talking about the big-scale universe, or talking about what might be happening at quantum levels? You see, people talk about, I'm not saying anything about 10 to the minus 33 centimeter physics. If we're talking about the large-scale structure of the universe, again, I'm not saying anything about it. It does make a certain difference to the equations, which I didn't discuss in this talk. You see, you have to write down some equations about how the universe gets through the crossover surface from one eon to the next. And various people have written down equations, most particularly Paul Todd, who was first to consider these things. I had a set of equations, which were in one of our papers, and various other people like Jörg Freundiner have various schemes. They don't make a huge amount of difference to what happens. The main difference is that you do have a problem about making killing off some degrees of freedom when you cross over from one into the other. And the nicest way of doing killing off those degrees of freedom is having the universe having a compact topology. So that any of the, I think if it has a compact topology, you might have to look at it, but if it's a spherical topology, that would get rid of some of these ambiguities. It may not be the answer, and I'm not being, I'm not trying to be dogmatic about this. I don't see that it connects with the paper that you're addressing. It's the theory certainly allows different spatial topologies on the large scale if they're big enough. Sure, you can have different spatial topologies. It might be the deeper understanding of the theory would give you an answer to that question, but it doesn't. If this is talking about the very tiny scale, then it certainly doesn't address that at all, because I'm not talking about the physics at 10 to the minus 33 centimeters. I'm trying to say that you don't need it for cosmology. The crossover to the next eon, you can just get away with it. That you can use the metric from the previous eon and carry it through until you're after the Planck level, and that you don't have to worry about horrible quantum foams and things like that. You don't want things like that because they might mess up the smoothness of the next eon. That's the best I can do to this question.
Mm-hmm. So again, let me ask, so what are the degrees of freedom you think have to be killed when you pass this?
All right, that's a question of detail in the equations. It basically has to do with the symmetry. You see, in the remote future, you have a de Sitter symmetry. And your equations are sort of respecting that de Sitter symmetry. Whereas in the crossover, you have something like a Tolman model. So you would have a radiation-dominated cosmology. And the symmetry in the Tolman model is smaller. You have a 6-parameter group rather than a 10-parameter group. And so you have to kill off those extra degrees of freedom. Now, they could be killed off by the actual nature of the matter in the previous one. It would be nice to see them in the equations. Now, if the topology is a spatial topology, then you kill off those extra. I'm not sure whether you completely kill them off, but you certainly helps with the equations. It's a detailed matter of the equations, and I don't think I could say more about that.
Okay, thank you. That was good. Okay, so the next question is also to the referring to the passing of aeons. Is there a jump in the entropy from very large to very small?
Okay, that's one I can answer. The entropy is almost entirely in black holes, even now. Even now, the black holes dominate the entropy by an absolutely huge factor. So I'm saying that the entropy in the very remote future will be in the black holes. Now, the black holes will evaporate, and some of the entropy will get destroyed in the singularities. This is, of course, a big argument that people have about, do you retrieve the entropy? I don't think that can possibly be correct. So you have this problem with the repeating the no cloning theorem when you get up near the singularity, which is space-like, I should say, and you have a little problem with your getting close to that singularity, and you can't clone that somewhere else without violating no cloning. However, many people believe that you've got to retain the information in the black hole. If you do retain that information, it's no help, because it's all in the radiation. And if it's in the Hawking radiation, that is again squashed into that little tiny Hawking point. It makes no difference. Well, it may be, someday people may be able to tell the difference, because the nature of the Hawking point may well be different. However, just considering the entropy, that entropy is destroyed in the Hawking point. And you have a far smaller, the energy comes through, if you like, if you can do integrals around to see that exactly that there must be still a big contribution to the energy in the next, you have to do this correctly to take care of the conformal structure. But nevertheless, there is a big, something like energy coming through on the other side. But the entropy has to be pretty well wiped out in the Hawking points. So that's what happens to it. The entropy is enormous in the black holes and is basically wiped out in the Hawking points.
Thank you.
It's 10 to the minus 33 centimeters. You see, all that is squashed into much smaller. As you cross over into the next eon, it's much smaller than the Planck scale size. So that there's, who knows what the physics does, and I'm just saying that the entropy just gets squashed out of the picture.
Okay, thank you. So now let's move on to the next question. So there is the question in the slide on the equivalence principle and quantum mechanics. You set small t equal to large t.
Yes.
But that we know the time gets dilated in a moving reference frame.
The time, that's not a moving reference. No, there's no time dilation here. This is anyway, it's a Newtonian calculation. I'm not even considering special relativity here. I mean, I'm looking at a very weak field, and you're looking at, there's no time dilation here that can be considered. The t should be the same. It's not a relativistic calculation. Okay, you could do it more precisely if you like, take that into account, but that would be a very tiny effect. I'm only looking at very small movements. There's no high velocities involved in this picture, so you could get away with a Newtonian time t equals t. Yes.
Okay, thank you. That's okay. The next question. We have a great number of questions still to come. Let's see how far we get with it. So next question is, at the beginning of the talk, you mentioned the cosmological constant, but we currently do not have a definite value for it. Why is it so difficult to measure it?
So difficult to measure it? Well, it's pretty hard to measure because it's all you've got to go on is the expansion, the exponential expansion of the universe. So you have to have that determined to a very great precision. And you don't have any other things to compare it with. Maybe someday we will, but the cosmological constant is just taken from observation. And the observation is simply I don't know how many different features of cosmology now taken into consideration, but certainly initially it was the redshifts. They're looking at the supernova stars from the very distant ones and looking at the redshifts. But I expect there are, I mean, it's not something you can do in the lab, put it like that. You have to look at these cosmological parameters and get a good estimate for the cosmological constant. So I'm not surprised that it isn't determined to the sort of precision that you get for other numbers like the gravitational constant and things like that.
Okay, so let's do the next question. So here we have, you start with a lump with a mass m. You then put this mass into a superposition of two locations.
Yes.
So that we have two lumps in different locations. Each with
one lump, two locations. Yes.
Does this mean that an extra mass emerges into the universe when the superposition is created? Where does that extra mass come from?
No, it's a superposition of a mass in two locations. Now, this is standard quantum mechanics. I'm not doing anything wild here. You're looking at a mass. I mean, it could be a nucleus, you know. In quantum mechanics, you can have particles in two places at once. This is a very clear, puzzling implication of quantum mechanics. I remember hearing about it in Dirac's first lecture I went to on quantum, well, it wasn't the first lecture I went to on quantum mechanics, the first of his lectures on quantum mechanics, when he talked about a piece of chalk and he talked about it being in two places at once. And I remember not hearing his explanation because I was looking out of the window and not concentrating. So it worried me ever since. If you're talking about particles, nuclei, you know, quantum particles, sure, they can be in two places at once. It's not, the mass is not twice as much. It's the same mass, it's just that it's located, the wave function has a distribution which is concentrated in two places at the same time. And that can certainly happen in quantum mechanics. How that doesn't happen in classical mechanics is the problem which is one is trying to address here. Yes. Iraq, please talk. Yes, sorry.
Yeah, thank you. So maybe that we're now just on the quantum mechanics. Maybe Angelo, you want to pose your question now?
I have a question about quantum non-locality. You know, in quantum non-locality, somehow you have these correlations among space-like separated objects. Do you think that this can pose any problem in trying to combine in relativity to quantum mechanics at some point?
I think you're probably going to have to do the retroactive picture. You see, that's what I suppose it does, yes. That's why I'm saying there is a lot of problem unless, I think an important point is to make this distinction between the quantum and classical reality. So that the thing that you finally measure, I mean, it would be useful to look at the questions of the heating and the issues that I know people are very interested in, and how is that addressed in the kind of picture which I'm putting forward. I haven't looked at complicated systems where you have many, many things in complicated superpositions like that. And it would be important to address that. But my view is that the separations, I mean, certainly the picture one has, certainly in your paper, with I think about the paper with the, where you look at the gravitational expectation that you might have a heating. And this would certainly be in the particular model that Diyoshi has put forward, you would expect to see something like that. And the sort of cartoon I remember in the papers where you imagine a particle or a small system in a superposition of two locations, and then that superposition of two locations jumps to being in one location. And so this is effectively a heating because you've got something which is localizing in this sense. But if the localization is taken back to before it separates, so that would be the classical reality picture I have, then you don't get the heating. But that needs to, I'm just waving my hands here, and I'm certainly agreeing with you, I think, that it needs a proper theory to see how to bring that into a scheme which describes a whole slew of collapse processes taking place all the time. Because certainly in a gas or in a fluid or something like in a liquid, you would expect the reduction process to be happening all the time. I imagine in a gas, sure, at some points, then the superposition between different spacetimes must reach a place where the particles start to localize. And certainly that happens when you have maybe a crystal forming out of a vapor, and it localizes itself out of what was originally a superposition of being in different locations. And so you've got to have a good theory which tells you that that localization happens without the heating. And the claim I'm making is that you have to have a theory in which the localization keeps going back to before the separation took place. And you have to make a sensible theory of that, which doesn't violate ordinary ideas of causality and so on. I don't think it does you see, when I take the kind of model I have, I've thought about it quite a bit, and you don't get any obvious, you can't sort of, go back and shoot your grandfather as the usual kind of problem people have with retroactivity of this sort. It's a more subtle kind of retroactivity. It's only making a choice between superpositions. And that choice, you might think it's made later on, because that's when the quantum reality has to stop being the reality in a certain sense. And it goes back to having made a choice, one or the other. And that needs to be spread out into a genuine scheme, which can treat the kinds of things that you look at. Absolutely, and I agree with that. And it's a missing part of the theory as things stand. Yes.
Thank you.
Okay, the next question is connected to this one. So it says, in your theory, the wave function or quantum state seems to be the complete description of a system. What happens in between collapses? We still have a superposition, hence a measurement problem. Is that correct?
Well, the quantum reality is given by the wave function, yes. But then it jumps. The quantum reality becomes, when it becomes too classical in a certain sense, when the gravitational field becomes too, another way of saying it is when the Ford volume between the choices between the space-times becomes of order unity. That's another way of saying the Diochy type of criterion here, that the Ford volume between the space-times becomes one unit approximately. It's not also it's only an average of 1 unit Planck 4 volume, but then it has to become one or the other. I'm not quite sure. I think I strayed away from the question when I said that. Can you remind me what?
It was about what happens in between the collapses. We still have a superposition.
Oh yes, you have a superposition. That's right. Yes, the quantum reality is there is a superposition. Yes.
But do we then still have a measurement problem in between?
Well, the measurement. I see. I think I see what you're saying. Now, the measurement always involves a. You see, whenever you make a measurement, you are converting something into a macroscopic thing. And I'm claiming, even if it's where a pointer points on a dial, that pointer will be big enough to collapse the state because its gravitational field will be big enough. It doesn't take much. When you look at the separation between the, you might say this is a pretty small energy, but it's big. So you think of it as compared with a Planck energy. A Planck energy is big. A Planck energy is a sizable explosion. It's an artillery shell or something like that. That is a Planck energy. Now we're looking at tiny, tiny energies compared with that. So for a Planck energy, the lifetime would be Planck time, roughly speaking. So now you're looking at energies which are very, very tiny. So if you want you preserve the quantum superposition for a long time, because the energy, the uncertainty in the energy, if you like, is very small. But that correlates to a length of time in the superposition. But any measurement, say it's a pointer or something going one way or another, it has a gravitational field. And if it's just a little pointer and a little dial, that's huge. That will say that the reduction time would be a tiny fraction of a second. That.
So there are two related questions to this. So
yeah.
Maybe I read, the first one is, you mentioned that you are inclined to consider collapses as instantaneous, which is the physical motivation leads you to this conclusion?
That's a good question. I think I couldn't make sense of it relativistically otherwise. I was probably a little too soon at making this choice, because when I looked at, I wrote an article recently which I looked at this more carefully, and CSL type models can get away with it. You have to modify quantum mechanics in a certain way, which isn't much of a modification. You see, you have to say you have a superposition of a body in two locations, and according to the CSL models, the sort of Philip Pearl type of situation, you've got amplitudes attached to each, and these amplitudes jiggle around until one of the amplitudes jiggles around to be much smaller than the other one, and then you say that more or less the collapse has happened. It's never quite clear to me because when it's really happened or not. I think that was one of my troubles. But let's say that you take that model, it just jiggles around until one dominates over the other. Now, it doesn't work if you have to normalize these things to, say, the sum of the squares of the amplitudes, squares of the moduli of amplitudes is 1. But it does work if you say you don't care about normalizing, and you just say the amplitudes, you're looking at the ratio of the squares of the moduli of the amplitudes. And one of them can fade away and the other one is still there. And if it's that ratio, you still get a consistent picture in the one I'm doing. Where you don't get a consistent picture, and I didn't talk about it here because it would take me too far afield, is a very ingenious argument due to Sandro Donati. And Sandro, I'm sort of extending his argument. The argument is that if the rate of collapse depends on the amplitudes, you're in trouble. That's basically what he's saying. That if you have a certain amplitude of the state being at position A, amplitude alpha that it's A, and amplitude beta that it's B. Now, if the reduction time to either A or B depends on the ratio of alpha to beta, then you could do an experiment which would enable you to send signals faster than light in the Alice and Bob situation. You look at the EPR type of situation, and you can send a signal faster than light if the amplitudes, the ratio of the amplitudes could be detected. So you have a system which tries to say how long does the reduction time take.
Okay. Yeah.
And with, I think, the CSL models, if they're gradual, that you see, you could get a measurement which would tell the rate of the amplitudes. And so this would tell you that the reduction time has to be instantaneous. So I think there is an argument. This is not in anything I've written down. Well, it is written down in the notes I sent out to various people. Yes, it is written down. It's not published. That if it's not instantaneous, you can send signals faster than light. Yeah.
Okay, so maybe there is a follow-up question.
Yes.
Regarding the retroactive picture. When
Yes.
you rewind the state back to before it went into a superposition.
Yes.
What does the system do after that point? Does it keep evolving in a quantum way and spread back out? That seems bad. Or does it evolve in a different way? And if so, what's the physics of that behavior?
Well, the physics is the classical. When the retroactive thing, you see, it spoils the quantum superposition that you were having before. That's why it's retroactive. You see, the quantum description has a superposition between the two locations. But then when one of them disappears, and the quantum reality has relinquished its hold on the state at that point, you have to go back to the classical reality, and the classical reality is one or the other. Now, there could be quantum parts of the system already in that classical state. So it's only reducing some degrees of freedom. There may be other degrees of freedom which haven't collapsed yet. That's true. I mean, it requires a bigger theory than one has at the moment. But the picture I have is that the quantum reality retains the superposition, but when the collapse happens, you have to go back to the last measurement that was made, basically. And if you try to measure this is a sort of paradox here. You try to measure whether the superposition was actually there by using Einstein's dictum, and then you've already made a quantum measurement, so it has to go back to there, not to the earlier one. So you see, you have to go back to the last measurement that was actually made. The measurement is only made when there is a collapse of the wave function. All measurements are like that. So all measurements take place because the wave function is collapsed to one thing or the other. And the collapse always takes place in this scheme because there has been mass displacement, whether that's in a pointer in a dial, whether it's in something else. It may be, goodness knows what, a piece of paper which has become stained because of because something has gone one way rather than the other.
Okay, thank you. There is a more general question now.
Yes.
So, what are your thoughts on the many world interpretation of quantum mechanics?
Well, my answer is no. My answer is it's a good experience in life to have gone through a stage in your life where you believe in the many worlds theory, which I did at one time. I can't remember how long it lasted, but it's a good thing to reject it. So my view is that the many worlds interpretation is not correct, and that all these worlds do not coexist, and that one of them collapses out. You see, I had always trouble. You see, you believe in it for a while, and then you try to understand what your consciousness is doing, threading its way through this. And as your friends all disappear along different routes along, it's rather disappointing. It's rather an isolating view. No, I think it's a scheme that you have to consider at some stage in your life and then reject. That's what I consider. Yes.
Thank you.
Okay.
So now it's a question regarding your twistor theory. May a twist us give some insight with the measurement problem is the question.
There's a good question. I hope so. There is a piece of work done by a colleague of mine. He's done most of the work, I should say, on this. And other people's names have knocked it out of my head now. Danajski. Maciek Danajski, who is a Polish chap working in Cambridge. I'm not sure where he is during the lockdown, but he and I have been trying to work on a Newtonian. This is a sort of Newtonian version of twistor theory. It's not real twistor theory because it's too hard to do it. But if you look at the Newtonian version, where the speed of light is considered to be infinite, and then you can make a model where you model the collapse of the wave function. The idea is that twistor theory would have something to say about it eventually. The point of view is basically this, that in twistor theory, the space-time is a secondary notion. You have basically it's a twistor algebra. You have twistor geometry, but when you're trying to do full general relativity, you need to have this twistor algebra. And there are certain subalgebras in this algebra which define points in the space-time. And the idea is that these space-times would, when they get too quantum mechanically distorted, that is like a superposition between different space-times, then the thing would jump from one to the other. It's not impossible because you can see that if your space-time is is secondary. You see, there was the first time in twist theory where you could actually talk about curved space-times was in a thing called the nonlinear graviton, which was a complex space-time. So it's not really real space-time, but it gives you a good picture that the space-time points are, you have this twistor geometry, which is a 3 complex dimensional space. And you have lines in this 3 complex dimensional space. If there's no curvature, these are straight lines. And these straight lines give you the points in the space-time. So the space-time is represented by these lines. Now, when you have a curved twistor space, then you still know what you mean by the straight lines, but you may get so curved that they start to disappear or they jump or do something like that. So the idea is that the points in the space-time being secondary can disappear or jump or do funny things when the quantum space-time becomes too distorted. Now, this is just a hope, but you can see part of that hope realized in this Newtonian picture, which Maciek Danajski has developed in conjunction with me, but he's done most of the work, I should say. And you do get a picture of a collapse of the wave function, which is sort of the kind of thing that one's looking for.
Okay, thank you. Now we have 2 more very concrete short questions, I think.
Okay.
One is considering the conformal cyclic cosmology theory, is the total amount of the energy of the previous universe the same as the next one, or may they be different?
You have to be careful about the term energy, because energy is not the right concept to use. It depends on having a time-like killing vector, and all these time-like killing vectors get squashed into points that cross over. It just doesn't work. However, you can do something which is putting this in a broader framework, which is looking at a conformal framework, and you can talk about energy. It's not quite the same notion, but it's good enough. And you can do integrals over closed space-like 2-dimensional surfaces and work out what this energy is in that surface. And you can carry that across the crossover, and it conserves itself. So it's conserved as you go across. So I think the best answer I can say to this question is it is conserved as you go across, but you have to talk about the right concept. This concept of energy is conserved as you cross over from one eon to the next, yes. So there's no loss of energy or anything like that. The entropy is the problem where you have to sort of renormalize it. It just gets squashed out. All the entropy in the black holes gets lost in the Hawking points. And it comes, I should say it's a different point of view from one that I expressed before thinking about the Hawking points more seriously. But I think this is the correct point of view in the CCC model. But energy, yeah, there is a concept of energy, you have to be careful about it, which is conserved as you cross over from one eon to the next, and it keeps on going, yes.
Okay, thank you. So now, basically, we did the half-an-hour general discussion session. I don't know if you still want to continue, because I mean, the list of questions is getting longer and longer. It's not even, finished. But
I'm all right. I didn't know if I'm interrupting some other talk or something.
At some point, I don't know. One might also.
It's up to I can go on. I'm still standing. Well, still sitting.
Okay, but you have to tell us then also if you get tired.
Maybe we just have a few more questions and then we have a limit.
Okay.
Okay, let's say maybe 10 more minutes, if it's fine for you.
That's fine. Yes, sure.
Okay, it's getting more and more questions here. Okay, so now the next question. Do you have a time scale for the separation of eons?
I have to understand the question here. The one eon follows immediately on from the one before, so there is no separation.
Yeah, but how long does one take?
Well, it's an infinite time. The time is technically infinity. So I see. You might say, how long does the eon last before it gives up on being?
Yeah, exactly.
It's just that the notion of time, you see, becomes more meaningless. You see, yeah, let me answer the question a little better. You see, what is time in this scheme? I did talk about clocks in my picture with the light cone, the null cone, and I had the two particles zipping along, and they are measuring as they hit these different space, like the hyperboloid looking surfaces of one tick and the next tick and the next tick. And these are defined by the mass of the particle. When you have a definite mass, you have a definite clock. So this is the point that I was emphasizing there. So as long as you have mass, you have clocks. Now, if you have mass fade out, which is what I'm saying in the remote future, the clocks begin to lose their meaning, particularly if the fade out is different for different particles. And I expect that it would be, because mass, I'm not a particle physicist, so I get this secondhand, but my understanding of the mass of a particle is it's really quite a complicated thing. You have a Higgs mechanism, and then you have all sorts of things to do with baryonic so-and-so, and I'm not going to say this because I'll show my ignorance when I start talking about it. But my understanding is that there are many, many different features which in standard quantum mechanics or standard particle physics determine the mass of a particle. The Higgs mechanism being one of them, and you have other features as well. Now, I suspect it's quite complicated, but the mass fade out will be fading out differently for different particles. So there might well be a time that is not infinite, because the mass fade out would give you different times for different particles. I have no idea what it would be. And it needs a theory of mass fade out, which we don't have as things stand. So I can't answer the question, because my answer would really be, I think that the time begins to lose its meaning.
Yeah,
because you don't have a clear notion of mass to give you clocks. And therefore, although I'm saying it's infinite if you use the cosmological constant. You see, somebody asked me before, why is it so badly determined? Well, because you don't have much to fix it. But I am saying that it is fixed in this theory. So although mass will fade out, the cosmological constant does not. It is something which is fixed in the theory, and I guess it would give you a time. I think the time may well be infinite. I'm not sure. I haven't done the calculation. That's a good question. Is there a time? There's a conformal time. Yes. You see, when I say a conformal time, that is how, if you take a point and you take a particle or a world line, so just like a world line, and you extend it into the future as far as you go, and then it looks back, and its event horizon will encompass a certain amount of the universe. And that amount of universe is a definite amount. So that could be said, and that could be translated into a time. So I suppose in some curious roundabout sense, I could give a time, but I haven't done it, so I can't answer the question. But yes, there is a sort of, you have to draw the conformal diagram, and you can see you write the conformal infinity as a definite place. It's not, it's the ticking of a clock may get very rapid as you approach that, but it's a definite place, which is a definite time in quotes. And that time is time infinity, if you like, in the probably cosmological constant time. And then it becomes the zero of the next eon. Yeah.
Okay, thank you. So you're ready for one more question?
Yeah, I suppose so. I hope I can have a clearer answer than that one. Yeah.
So now we have a question about the pilot wave theory. Do you think the pilot wave theory could be a pertinent answer to the measurement problem in quantum mechanics?
We're talking about Bohm or Bohm-Hailey?
Yes.
You see, I always have a bit of, I mean, I used to talk to, I used to spend a lot of time at Birkbeck College, and so we had many discussions with Bohm. So I certainly got to know him quite well. Whether I got to understand his theory well enough, I'm not totally sure. But the picture I always had with the theory was that it didn't change quantum mechanics, even though somehow all the probabilities of what it was going to do were inbuilt, that somehow it knew which decision it was going to make when a measurement was made, in some sense. I mean, you had these two different, I'm not sure I can talk off the top of my head about it now because I've thought about it for a while, but I felt it didn't resolve the answer. It didn't resolve the problem of the state reduction. Roughly speaking, the answers to which way a particle go in a two-slit experiment or something were inbuilt in it. It sort of knew ahead of time which way it was going to go. With quantum potential or something, it was telling it which way it should go, but it had to be traced back to right back at an early time. I didn't find it really terribly helpful in telling you when the reduction would happen, and it wasn't motivated by general principles of general relativity, which I consider that the arguments I put forward are motivated by. So although I had been acquainted with it, and I'm afraid I've rather forgotten most of the native, I could probably recall them with some detail, with some effort, but it's certainly different, and I don't think it relates to gravity at all, certainly not the original scheme. Whether Hailey was able to make it relate to gravity, I can't quite remember now.
Okay, so there is, I think, a follow-up question by Dirk. So if you like to, I think we should then make it the last question, because we still have many questions from the audience, but I fear we cannot go through all of these.
Well, do what you like. I'm still all right, so don't worry about me. It's just if my answers are getting more rambling, it's just that I can't answer the questions.
No, it's very well also appreciated that you take so much time today for us. So I just thought, so when you introduced the classical reality and the quantum reality,
Yeah.
I was a bit worried about how serious this distinction is made. And I want to ask the following question that helps me to understand this better. If I think about classical electrodynamics, then I would also see, in view of the questions that you use to distinguish these two realities, in classical electrodynamics, if I put a charge on a table, I wouldn't know what the field is without asking the theory. So, of course, the theory tells me it's a Coulomb field. However, there's no way I can measure it. So I would have to put detectors everywhere in space to measure it. So my question here would be, would you then consider electrodynamics already quantum because it fits more into the question? Yeah, you could say, well, if I measure the field here, it should have this and that value, and for certainty, you will also measure it like this. Or would you consider it still more classical, where I then would ask again, what is really the distinction between these two fields?
Well, I think classical electromagnetic, radio waves and all that have to be considered as classical reality. I think, you see, there is a vagueness which certainly has to be there. The vagueness, I think of mainly the classical reality as the space-time, and many things don't move it much. So it's fairly undisturbed by details. But of course, if you get disturbances of a Planck scale, then that's a that's a limitation of how far the classical reality can be extended. That's certainly true. So classical reality is not utterly well defined. It's certainly not well defined at Planck scales. So I would have to say it sort of averages over that or something. When you talk about an electromagnetic field, I certainly think of that as classical reality as long as I'm not, there are lots and lots of photons around. If it's like a radio wave, it's pretty classical. If it's even like ordinary light and I'm not doing diffraction on it, it's pretty classical. But it's not moving the space-time very much. It's a vague distinction. I think the distinction is more in the ontology. I would say if you can ask a question, can I measure it? Then it's classical reality. I mean, can I say, what is your state? So I can say, what is the electromagnetic field? You can do a pretty good job on that. Then it's classical reality. If, as you say, you're looking at the electromagnetic field of a single particle, then you might be in trouble because it's really too much of a quantum system there. And you can't really ask, what is your state? You've got to make a measurement and you've got to have a good idea of what its state is already. And you might confirm your question. So that's quantum reality. So I think the distinction is probably not as clear cut as I was probably trying to make in my talk. I'm admitting that it's probably a vague kind of limit in both cases. Certainly the quantum reality is a limit already because the Einstein dictum is already confuted by the reduction time. Because always there will be a lifetime. If you're trying to disturb the space-time as little as possible, it might take the age of the universe before it does one or the other. But still, it's giving you a slight uncertainty in the with certainty in the Einstein statement. Can you say with certainty that it confirms? So there's always a little bit of a fuzziness on the with certainty. So there's a little bit of fuzziness on the quantum reality for that reason. And there's a bit of fuzziness on the classical reality for the quantum determination of the space-time to that precision. And whether that's the same as whether a classical electromagnetic field can be considered as classical, because its effect on the gravitational field is going to be pretty small normally. Whereas you still like to think of it as a classical field as long as you're not doing quantum mechanics on it. I think there's a vagueness on both sides, and I certainly agree with that. I think, nevertheless, it's a useful idealization to think of these two different realities. I was rather driven to that when writing my notes. These notes which I sort of circulated to various people, and I'm quite happy to add people's names to the notes. I have to rewrite them now, though, because various things have changed the way I think about them. And the main thing which has changed is to make this distinction between quantum and classical reality, which I didn't even think of until quite late. And so I think that notion has to be introduced quite early, so one can make clear.
Okay, thank you. I think this answered also many of the questions which still come to be, or which are still on the list. So I think this would be a good place to end this session. And thank you very much again for that beautiful talk and that you took the time and went through all the questions. And yeah, I hope to hear from you. And yeah, I will now, Dirk, you will announce now the follow-up session. Thank you.
Thank you. My pleasure. Thank you.
Yes, Penrose, that was a really amazing talk and amazing patience you had with us, which is greatly appreciated. I will stop now with a couple of general announcements. I think most of you know already our website. This is probably the place how you found us. The spring series schedule, which I couldn't show before, is already quite planned out. So we're going to add all the titles and the abstracts really soon. The sessions will always be announced as it was here. There will not be a single link, but we'll put each link in each session. So next time we'll meet with Robert Wald and Michael Kiesling, and we'll have a lot of talk, I think, about electrodynamics, both classical and quantum, especially also the self force or self reaction problem. And then we continue with more talks about gravitation and more talks about foundations in quantum mechanics. So as these session themes arrive, we will make a bit more clear what we actually mean behind these names. So far, they help us to collect a little bit the topics of the speakers so that we can have a nice panel discussion in the end. All right. So I'm very thankful, Sir Penrose, that you took the time. Very thankful for all the attendees. As I told before, some of the meetings will be smaller, where we'll really convert this into a meeting where we can really discuss also face-to-face. But these big meetings like today, we have to take as these in this webinar format. Just to let you know, today we had around total 650 attendees. Among those, we could only get through, I think if I round it up, more or less, I don't know, maybe 25 questions or so. But I think in the smaller meetings, that we might even get some face-to-face time. Okay. Angelo and Ward, do you have any final words for this session?
Oh, just want to thank you and Paula for the great job, and of course also Roger for the very nice talk.
Thank you.
And I second that. Thanks a lot.
Thank you very much. It was very good to see each other. All right, then I will close the webinar now. You should be join later on for a little in discussion, or only as panelists and Sir Penrose, if you like. Yeah, you could just rejoin after I stopped. Okay, thank you everybody for joining, and hopefully see you next time. Goodbye and stay healthy.